Good morning, everyone. Thanks for joining us. It's glad to be here to give our topic. And I'm Zhihao Xu from Alibaba Cloud, and I'm currently the maintainer of a CNCF sandbox project called Fluid. Fluid is a project related to AI and storage. And the co-speaker here is also from Alibaba Cloud. She is now the maintainer of Alibaba Cloud's object storage services CSI driver. So in the next half an hour, we will share our experience on how to orchestrate volumes for remote storage in cloud-native AI scenarios. Our topic today will be divided in 4 parts. The first part is a scenario part. We will ask questions like how to make users easily access remote storage in an AI platform. The AI platform is probably built on Kubernetes. And the second part is the problem part. We will present some problems like what is a common practice, for data accessing and why it needs more refactoring to fit into cloud-native AI scenarios. The third part is our solution. We are going to demonstrate our solution with some slides, and we'll give a pre-recording video to show how it works in a real Kubernetes environment. And the last part is more like a discussion. We will talk about some special user requirements we met, which are not easy for Kubernetes CSI to solve. And we will introduce the project Fluid here and try to talk about how Fluid wants to solve it with some attempts. So let's start with a user story. Imagine you are a platform engineer and your job is to build an AI platform for your data scientists in your company. To give a best user experience, you may want the platform to provide out-of-box developing environment like a Google Colab or using some technology like VS Code Web. It's not an easy job, especially if you want the platform to be both user-friendly and resource-efficient. Kubernetes is a mature and great choice to manage computing devices like GPU devices. But the question is, that's just the computing part. What about the storage part? Data accessing is very important for any AI workloads, and data can be stored in some remote storage, for example, like object storage or NAS. So what is the best way to orchestrate volumes on Kubernetes for such AI platform users? We're talking about how to orchestrate volumes in a Kubernetes environment. So if you look at the Kubernetes community, you may find a recommended way to do this is to mount the remote storage to your containers with a combination of persistent volume, container storage interface, and file system in user space, aka Fuse. You may find lots of storage systems like Ceph or cloud providers. Object storage gives similar technical architecture to integrate themselves with Kubernetes. So the picture here shows a simplified process of how it works. Actually, the workloads here, a workload pod is going to start on some node. The CSI node plugin will know it, and it tries to start a Fuse client process on the host. The Fuse client process is actually a user space process. It mounts remote storage at a specific host path, and the host path will be then bind mounted to the container's volume path. Fuse, the file system in user space, it translates remote storage to a POSIX compliant file system. So any operation, any data operation, on that file system will be mirrored as some data operation to the remote storage. So now the workload pod is able to access remote storage just like it is accessing any files stored at a local file system. But is that a good practice? Is that good enough for our AI platform? In our practice, it's good, but it can be better. We found many issues of this solution, and most of them come from the host running Fuse clients. Firstly, AI workloads put heavy pressure on Fuse clients. They consume extra CPUs and memory resources on the node, but Kubernetes is unaware of it. For example, the node, you may find some situation like you find a node with very high load, but the port limits on that node only occupies about 15% of the resource on that node. And secondly, Fuse client involves with new features and optimizations. Different versions of Fuse clients lead to dependency conflicts. For example, Fuse clients for S3 bucket and for Alibaba Cloud's object storage have different versions of live Fuse dependency. That means it might not be a good idea to start them both on the same node because there might be some compatibility issues. Thirdly, it is hard to diagnose a host running Fuse client. Fuse client, actually, we talked about before, it translates a remote storage to a local file system. So the error message reported by the Fuse client, by the file system, can be unclear and annoying. For example, here we can see the file system reports a permission denied error here. But we cannot know what the root cause is without checking the Fuse client's log messages. Because the Fuse client is running on the host, so we cannot easily to check its logs. You may have to log onto the node, find the process number, and check the log message of the process number. So the last is about a coarse-grained authorization. Two Fuse clients running on the same host will always share the same IAM binding to a Kubernetes node. So it's not possible to isolate the data permission among different users. So all these issues make us rethink about it. They look like the same issues. They look like the same issues encountered when we are running a non-containerized workload. So a simple solution would be, why not running Fuse clients in containers? But how can we run Fuse clients in containers? In the host running version, this is a recap of the host running version, the CSI and the Fuse and the persistent volume combination. CSI launches a Fuse client process every time a workload port is scheduled on that node. So here's our modified version. When a workload port is going to start on some node, instead of starting a host running process on it, CSI launches a Fuse client port on that node, or it can inject a Fuse sidecar into the workload port. This Fuse container starts by mounting remote storage on some passing container, and the mount point will be propagated from the container to the host path. So CSI will check if the mount point on the given host path exists. If it finds the mount point, it means the Fuse port is successfully started. So CSI can bind mount it to the workload port's volume mount path. Containerized Fuse clients help us solve the issues mentioned before. Firstly, we are now able to set in container CPU and memory requests or limits to control its resource consumption. Fuse port will run in the Kubernetes world just like any other workload. And the second problem is the dependency conflicts. Dependency conflicts will not be a problem again because they are packaged together into container images. This is a natural advantage when we are using containers. Also, it is easy to check Fuse log message to know exactly why error happens. You can simply use tools like kubectl logs or logtail to check containers log messages. So there's no need to log onto the node, find the process number, and see its std out or std error. And finally, containerized Fuse clients can leverage container-level access control like the AWS IAM roles for service accounts, aka IRSA. IRSA binds permission to a pod's lifecycle, so once the pod is deleted from the Kubernetes cluster, its credentials will also be removed, so it makes a fine-grained permission control. So this is my part, and welcome.
Okay, thanks for the sharing. We can summarize that to run a few clients in a container allows better management, but does this mean we can access the data just like local storage? Some of the experienced Kubernetes engineer who have such impressions that the remote storage volumes, or more especially the object storage volumes, are a little bit unstable. In the online AI platform scenarios we mentioned earlier, a data scientist might suddenly encounter such not connected error here. Mostly is caused by the Fuse client's crash. Unlike the kernel file system, the Fuse clients may corrupt for many reasons, like the OOM or the unexpected segmentation fault. The former is quite common in AI scenarios from our experience. And sometimes we want to restart the Fuse clients with different parameters too. The Fuse clients run in the containers seems can be restarted easily when it's crashed, but this doesn't equal to the recovery of the data accessing from our workloads to the remote storage. If already know it's CSI who is responsible for mounting the mount points between the Fuse clients and the workloads. But CSI cannot be aware of the disconnection issue. This means our users can only restart the workload to invoke CSI. This may cause all the previous development of the training or the training process to be wasted. Introducing an additional operator can be an intuitive way to take charge of our mount points. As the figure shows here, the operator works as the daemon sets in cluster and keeps carrying the mount info on nodes. If you try to remount the corrupted mount points, it can recover the mount points in the workload containers if the host to container mount propagations is allowed. It's not a strictly real-time method, and carries inter-rows needs to be well considered, but this method is compatible with any Fuse clients. However, in production practice, we found that this approach may have some limitations. Every time the remount happens, it will leave a broken mount point on node, and if the Fuse clients exists frequently, the huge amount of the mount points may take the extra overhead and make the performance of the nodes worse. Unfortunately, the operations cannot easily clean these residual mount points because it's in a different mount namespace than the workload. Therefore, we propose another solution, which requires our Fuse clients need to be developed based on the Go Fuse or the Live Fuse 3.3.0 or above. They will have such capabilities, allowing open depth Fuse file descriptors, or called the FDs, to be passed via the mount points of the special format like this. This means we can use the CSIs to open the depth Fuse first, create the mount points, get the FD, and create the mount points in advance. Then we introduce the mounters here. It works as a daemon process in the Fuse client's container. It gets the FD from CSIs and start the Fuse clients with the FD. The Fuse clients will reuse the mount point CSIs pre-mounted before. These mounters will keep the FD in memory and keep watching the status of the Fuse client. So when the client crash, the mount point is broken, the mounters will restart the clients immediately with the same FD again. During the recovery process, no new mount points are created, and there is no residual mount point issue. Also, this is a relatively real-time solution. There's nearly no modification cost of the Fuse clients in both methods we mentioned above. but they are not perfect in love due to the lack of the section's context recovery. Users might feel the crash of the Fields client shortly and need to retrace when the I/O requests temporarily fail. In the following demos, we will quickly check out how the pre-mounting methods works and its effect. Okay. We have prepared a demo based on the online VS Code platforms deployed in the container. In the demo, we will simulate some common exceptions and show how we solve them. Does this begin? OK. Let's check the templates of the PV and PVC first. Here's some basic source info like the bucket names and the path. It's a simple MIST dataset. We can see there is no reference to any secret. We just announce the authorization type and the role we will use. We use kube control to create them and track if they are bound as expected. The role is granted to the specific service account, and we do not set the resources request and limit. The default settings will be used. Okay, then let's also check the templates of the VS Code pod quickly. The PVC OSS is the PVC we created before. We mount it to the root data MMIST path in the container. Okay, so we create it and wait until it's running. Now it's running as expected. At the same time, our field port is running too. We post forward the 8018 port to the local host. And here's our online VS Code platform and the related data in the remote object storage service. Now we try to create a test file. It's failed with no permission error. In fact, it can be caused by various reasons for the no permissions error. Without the logs of the Fields clients, we can't even tell if the Linux user has no right access to this path or the roles permission is too limited. But because we run the Fields clients in a pod, we can check its logs by the kube control logs easily. It seems like a response from the service, and the messages is access denied by the bucket policy. It's clear, so we can go to the console of the service and find the related policy. Is here. It bans all the put object API, which will prevent users writing data. In this demo, we just delete it simply to fix this issue. Then let's try to create the text file again. We also write some words in file and save it. It seems successful. Okay, now we are going to simulate that the Fields clients crash unexpectedly. First, we get into the Fields container, which contains the mounter daemon process we mentioned and the running Fields clients. Okay, so we use the PS comments to verify it. Then we kill the Fields client process. So what happens in our VS Code? Okay, we should just kill that. Then let's check the VS Code platform. We find the data under the mount path disappear, but we get it back after a refresh. The saved data is still here. Finally, we can check the PID of the Fuse client. Okay, so it has indeed changed. The demo is finished. No.
Thanks for the demo, and that's a demo about coding a developing environment like VS Code. So we can go a bit more further. In our practice, we find many data scientists want to add some new data source into their coding environment. For example, you may want a new data set to be used to fill some machine learning features into their models to improve the performance. Also, we also found the performance, the data accessing performance is important because machine learning processes large amount of data to find the underlying pattern. So we need a cache layer here to improve the data accessing speed. So that's why we want to introduce Fluid, the project here. Fluid is a data orchestrator for cloud-native data-intensive applications. Fluid wants to introduce two key concepts to extend the persistent volume plus CSI framework. The first concept is dataset. Dataset is a mutable custom resource which describes a collection of data sources, while runtime is used to describe how to access the data defined in dataset. So, for example, you can use Fluid runtime to describe a life cycle of the distributed cache system. This picture shows an example of how data scientists can add new data source to their code environment with Fluid. What the data scientists need to do is to add a new storage URL to the dataset. For example, here we are adding a directory called ImageNet, which is stored in the S3 demo bucket. And the Fluid controllers will sync changes to the Fuse port. A manager process in the Fuse port will be notified to mount the new data sources. And a special file system called pass-through Fuse will be used here to mirror any changes from the Fuse port to the application port. So once our new file system is mounted in the Fuse port, the content changes will be propagated to the application port. So finally, data scientists will find themselves here a new directory mounting the new file system with content like in the ImageNet dataset to their developing environment. Fluid is also designed to help people set up a distributed cache system in their Kubernetes environment. For example, you can submit a custom resource called Fluid runtime. For example, like the right part of the on the slide. And you can define how many cache workers here, for example, 3, and how much capacity for each cache worker. For example, here we define it as 10 gigabytes. Cache worker is a component to manage the cache data, and while the cache master is a component to do service discovery and metadata management for the whole distributed cache system. Once you submit a Fluid runtime, Fluid will try to help you set up the distributed cache system. You can scale out the cache system when you want more capacity, and you can also scale in it when you think you don't need them anymore. Okay, so for in the last part of our topic, we can see a use case about how Fluid can speed up AI serving cold start. Instead of directly accessing data to accessing the remote wait files stored in a remote storage, a user can firstly scale out the distributed cache system by updating Fluid's runtime custom resource. For example, here we are setting the spec replicas to 3. That means we will try to scale out 3 cache worker ports. Then he or she can submit another Fluid resource called data load. Data load will trigger a cache warm-up job, so the model wait files will be fetched and stored into the cache worker ports. After then, the user can create or update its LLM serving deployment. to start rolling out of the LLM serving services. LLM serving pods will hit the cache when they are trying to read the model weight files. The distributed cache system is inside the Kubernetes cluster, so it's much faster than reading files from remote storage. In our experience, we can make the cold start about 5 times faster when loading an 8 billion llama model. And finally, it's also very easy to scale in the distributed cache system when all the LLM serving pods are ready. Because they are ready, there are no need to access the files, so the cache system can be scaled in. You can scale in it by specifying the spec replicas to 0, so all the cache worker pods will be scaled, will be deleted and removed from the Kubernetes cluster. And that's all about our topic today. And thanks for your attention. And let us know if you have any questions. And thank you again.